A tree data structure is a way to hold data that, when visualized, looks like a tree you would see in nature. Now, this is actually what we visualize a tree data structure to look like. All data points in the tree are called nodes. The top of the tree is called the root node, and from here it branches out into additional nodes, each of which may have more child nodes, and so on. Nodes with branches leading to other nodes are referred to as the parent of the node of the branches that leads to the child. Leaf nodes are nodes at the end of the tree that have no children. Also, any children of a node are parents of their own subtree. In this video, we will be covering a specific type of tree called a binary search tree. While the tree data structure can have any number of branches at a single node, for instance, see the C here? There's FGH, it has 3 branches at a single node. A binary tree, however, can only have 2 branches for every node. So look down here, here's a binary tree, each node only has 2 branches. Also, binary search trees are ordered. Each subtree is less than or equal to the parent node, and each right subtree is greater than or equal to the parent node. Because they use the principle of binary search, on average, operations are able to skip about half of the tree, so that each lookup, insertion, or deletion takes time proportional to the logarithm of the number of items stored in the tree. This is much better than the linear time required to find items by key in an unsorted array, but slower than the corresponding operations on a hash table. So let's see how this works in JavaScript. Here we're going to use classes to create the binary search tree. Basically we're going to create 2 classes, the node class and the BST or binary search tree class. The node class represents each node in the tree. And there's going to be 3 data properties. We have the data, which is what we're actually trying to store, and we have this.left and this.right, which are going to point to the left node and the right node. So in the binary search tree, we're going to have the constructor, which just creates the root node, which is the top of the tree, which starts as null, and then we're going to have the add function. So this is how we are going to add something to the tree. So we're going to add the data, we're going to get a reference to the root node, but if this is the first node will be null. In that case, we're just going to set the root node to the new data we just put in. So new node data. So we're just going to create a node based on that data. If it's not the first node, we're going to have to figure out where to put this node in the tree. To figure out where to place the new node, we are going to use a recursive function. So we're going to create this function, which is search tree. We're going to pass in the node, which starts off as the root node. If the data we pass in is less than node.data, that means we're going to put the node on the left side of the tree. So if the node.left side of the tree is null, we're just going to assign node.left to the new node, and then we'll return. But if node.left is not null, we're going to return search tree node.left. That just means we're going to continue searching. This is where the recursive nature comes in. It's going to run the search tree function again and continue working down the tree to find where to put the node. And you can see here, else if the data is more than node.data, that means we're going to put the node on the right side. So if node.right equals null, then we just assign node.right to the new node, and we can return. Else if the node.right does not equal null, we're going to have to keep searching. So we're going to return search tree node.right. So else, that means data is not less than node.data, data is not more than node.data, So they must be equal. If they're equal, we're not going to add the data to the tree. We're just going to return null. So this is the search tree function, and this is how we initially call the search tree function. Return search tree node, which starts out as the root node, but then it can be called with different nodes as it's going recursively through the tree. Let's say you have 50 in your tree and you have 17 in your tree and you want to add 23. First, it's going to see that the node is not null because you have things in your tree. And then it's going to run the search tree function, putting in the root node, which is 50. Then we'll see if data is less than node.data, which it is because 23 is less than 50. We're going to go to the node.left. If node.left is null, we would put it here, but it's not because there's a 17 here. Remember, we're just adding the number 23. So else if node.left does not equal null, which is true, we are going to return the search tree node.left. So we are now going to run this search tree function, but pass in the 17. So now we're going to see, is data less than node.data? Well, now data is 23, but node.data is 17, so this is false. Now we're going to go down to this. Is data more than node.data? Yeah, 23 is more than 17. Well, is node.right null? In this example, we're saying that 23 isn't there, so node.right would be null. And then we can just set node.right to be the new node. The next functions we're going to talk about are find min and find max. So we're just going to be finding the minimum of the array and finding the maximum of the array. If you look at this binary search tree right here, you can see the minimum is all the way on the left side, 9. The max is all the way on the right side, 76. So just using that knowledge makes it easy to find min and find max. So we're going to set the current node to the root node, and so the min is going to be all the way on the left. So while this .left does not equal null, the current node is going to be current.left. And then at the very end, it's going to return current.data. So we're going to check this. If the left side is not null, we're going to go to the next one. If it's not null, we're going to go to this one. If it's not null, we're going to go to this one. Now the next is null because there's nothing to the left of 9, so we're going to return current.data. We're going to return the 9 because that's the data on the very left side. Find max is just the same way, but the opposite. We're going to start at current, which is going to be this .root, which is going to start at the top, while current.right does not equal null. Well, this does not equal null because it's 72. Then we're going to go to the next loop, current equals current.right. We're going to go to the next one, but now current.right is null because there's nothing to the right of 76, so we can just return current.data. Now we have the find function. Now isPresent is very similar, but instead of returning the node, we're just going to return true or false whether the data is in the tree. So we're starting at the top, the root node. While current, that means while there is a current node, while current is not null, we're going to do the following. If data equals current.data, return true. That means we found it. If we haven't found it, we're going to see is data less than current.data? Now current equals current.left. So we're going to start searching on the left side. Else, well, data must be more than current.data. So we're going to start searching on the right side. And we're going to keep searching. And if we never find it, if we never find that data equals current.data and return true, that means it's not in the tree and we can return false. Okay, the remove function is a little more complicated than the other functions we've covered. Just like in the add function, in the remove function, there's going to be a recursive function. So we're going to create this function here, const remove node equals function, where we're going to pass in the node, and we're going to pass in the data, which is the data what we're trying to remove. So we have this whole function here, and then here's where we're gonna call the function at the end. This dot root equals remove node, and we're gonna pass in this dot root and data. We're assigning this dot root to whatever is returned to this function here. We're going to pass in the root node, because you always start with the root node, and then the data that we're searching for. So let's see how that works. First of all, we have to check if we have an empty tree. If the node equals null, then we have an empty tree, and we can return null. Now we're going to see, does data equal node.data? So we're trying to see if we can find that data in the tree. So if we've found the node with the data, this is what we're going to do. There's actually 3 different options. Either node has no children. That would be just like the 76. If there's no children, we just completely delete that node. So if node.left equals null and node.right equals null, that means there's no children. Just return null. When we're returning null, we're setting the node that had that data to null. Now we're going to check if the node just has one child. If node has no left child, if node.left equals null, that would be just like this 54 here. There's a node on the right, but there's no node on the left. If node.left equals null, then we're just going to return node.right. That means we're going to replace this node with whatever is on the right, which is 67. So instead of 72 pointing to 54, that will be replaced with 54's node.right, which is 67. And if there's no node on the right, we're going to do the same thing. We're going to just return the node that's on the left to be the new node that's being pointed to. It gets more complicated when the node has 2 children, like such as 17. If you want to replace node 17, you can't just put in 12 here, because then what will happen to 23? You can't just put in 23 here, because then what will happen to 12? So let's look down here at this picture down here. It's kind of small. Let's say we're trying to remove this 3 here that has the red X in here. The way to remove this node right here would be to replace it with this node down here. So if we remove 3, we can replace it with 4, and then everything will be right with the binary search tree. So if you look at what it would become over here, we just replace the 4 down here with the 3 up there. But how are we going to get down to that 4? Well, first we have to go to the right subnode, and then we have to go all the way down to the most left subnode after we've gone to the right subnode. So let's see that. We're going to create a temp node, which is going to be node.right. So in this case, the temp, if we're trying to delete the 3, the temp node would be node.right, which would be the 6 here. While temp node.left does not equal null, temp node equals node.left. That means we're going to go to the right of the node, we're going to delete, and then we're going to keep going to the left until we get to the last one on the left side. And this one just happens to be 4. There's no more to go down because you just have to go down 1. But if there was more to go down, it would just keep hopping down until it got to the most left node. Now we're going to set node.data to temp node.data. So the node is the 3 up here. So instead of the data of this node being 3, the data of the node is now 4 because temp node.data is 4. Now we're going to set node.right to equal, and now here we're going to call the remove node function again. This is where it starts becoming recursive, and we're going to pass in the node on the right and the temp node data. And this will keep running through the function and set up the right side of the tree correctly. We see here we were saying if data equals node.data, else if data is less than node.data. That just means we have to go to the left side of the tree because it's less. And here we're going to call we're going to say that node.left equals remove node, and we're going to call this recursive function again and pass in node.left and the data, and then we're going to return the node. Else, that means data is more than node.data. We're going to do node.right and then call this recursive function again and node.write data, and we're going to return the node. So you can see that delete is the most complicated one that we've covered, especially when one node has two leaves. So let's look at how you use a binary search tree, at least this one that I've created so far. So let's open up the console here. I'm going to do const bst equals new bst. I've created my binary search tree. We're going to add 4, add 2, 6, 1, 3, 5, 7. And then I'm going to remove 4, and then we're going to console.log the min and the max 2 times, and then we're going to check to see if 4 is present. Another thing we're going to do is I'm going to add in a remove 7, and we'll run that again. You can see it first, the minimum is 1. It's going to console.log max, which is 7, but then we remove 7. And now the max is going to be 6, and we're going to see, is this present? Is 4 present? False. Nope, 4 is not present because we've removed it. This video covered all the key methods common to a binary search tree. However, in a future video, I'll be going over a few other things you can do, such as finding the tree height and traversing the tree through in-order, pre-order, and post-order traversal.